Hello, welcome back. In one of the previous segments, we talked about the meaning of jump star percentage ESP instruction, the one that you're seeing here. Okay. What is the meaning of this instruction? It means that the control will transfer to the place where ESP is pointing to and start executing code. Okay, that is the idea of jump star ESP. All right, let's take this main function, right, which takes argv1 from the user input. I'm assuming argv1 exists, otherwise the program will crash. And of course, it's a good idea to check if arg count is at least 2. Even we can be more strict. We say arg count is equal to 2, then only proceed, otherwise don't. Assume argv1 exists. Okay, that is my point. We copy argv1 into the string copy buffer and return 0. Clearly, this is a buffer overflow problem, well known, nothing spectacular about this. However, the idea of this demo is to show to you that if you don't know the address of the buffer, right? Let's say the ASLR is turned on, therefore you don't know the address of the buffer. How can you leverage jump star percentage ESP instruction if it is present in the binary to perform an attack and bypass ASLR? That is the purpose of this demo. Okay. So the idea is that, of course, from the C code, you cannot tell exactly the memory layout. You would need to look at the assembly code. So I compiled it and I can now draw the stack layout for you. Okay. So the stack layout goes as follows. You would have your 80 bytes of buffer, right? You fill up some things. I'll tell you what to fill up here. In this case, actually, it doesn't really matter. Whatever you want, you can fill up 80 bytes of buffer. It will 80 bytes. And then for this particular assembly, you have the EBB. That's the caller's EBB, right? And you have your, the EBB itself is pointing to the EBB of the caller. That's the EBB base frame pointer. Okay. And then you have your return address. So this is the stack layout, which is drawn based on the assembly corresponding to this particular C code. Okay, this is the return address. Okay. So the idea of return to jump star percentage ESP is pretty neat. We replace the return address, right? We replace the return address by the address of jump star ESP in your binary. Somewhere in your binary, if you saw jump star percentage ESP, you replace that return address by this. Okay, by this address. All right. So what happens in that case? When this return statement runs, right? When this ret statement runs, what happens? Stack pointer is about to be going up, right? Ret means, what is the meaning of ret? Ret means approximately ret is same as pop to EAP. Okay. So that's the semantics of ret. That means the stack pointer will go up after the ret statement executes, right? Pop means go up after taking the data. So the stack pointer will go up. That means the stack pointer is going to point here after the ret statement is done. Okay. So what you're going to do here is that you're going to fill up your shell code in this area here. So this is your stack pointer, ESP, after the ret statement is done. After the ret statement of the main function is done, the stack pointer is going to point to the place where you put the shell code here. And the idea of this return to jump star percentage ESP is that when the ret statement runs, right, what is the meaning of ret? Of course, it will jump to the jump star percentage ESP instruction, and ESP is pointing to some shell code. So all of the shell code that is present here will start execute. Okay, so that's essentially the idea of jump star percentage ESP, and I will explain you the construction of the payload now. Okay, so let's go ahead and do that now. So of course, you need to disassemble this thing. I have made some assumptions on this binary. I have disabled the stack protector, which you should not do. I have enable the executable stack permission, which you should not be doing in general, just to get across the idea of jump to ESP. Okay, so here is your disassemble of main, and I draw the stack layout based on this disassembly after analyzing it offline. And there is a function I mentioned, is called jump to ESP. Okay, jump ESP instruction, and you can see there is a jump percentage star percentage ESP, which is at this location, right? That means I can copy and paste this as part of my return address. Essentially, that's what I'm doing in my Perl script. So I created a Perl script called exploit BSS, not BSS, sorry, the jump to ESP, right? And here is your shell code, which is the 24 bytes of shell code in this case, which I got it from internet, shell code database. And then I replace the return address by the address of jump star ESP instruction. If in your binary you see somewhere jump star ESP, you can leverage that address. Okay, it must be an address that doesn't change after the linker and loader and all those things loaded. So which is true for things that are part of the code region, right? Usually you don't randomize. Usually code is not randomized, even if the ASLR is turned on. If code is also randomized, then this is not going to work, of course. And then you fill up some knob to, okay, I'll explain why 84 knobs in a moment. But essentially the idea is fill up 80 bytes of your data and then 4 bytes of your EBB. So that's the reason why you have 84 bytes. And then the return address, which is this number, which is the little Indian representation in my case, and then the shell code. Okay, as you can see here, the shell code is above the return address. Okay, and then we write it to a file and execute the code. So Perl exploit JMP this, and now we can even use hex dump to look at the payload for this thing. As you can see, I have a lot of knobs, right? And then the return address, and then the shell code. The shell code is above the return address in this case, because when ret runs, ret is going to point to pop EAP instruction, which will move the stack pointer up, which means the ESP is going to point to the place where the shell code is. This is exactly the place where we are putting the shell code just above the return address. And then when ret runs, it's going to jump to the ESP and start executing the code. Okay. That's the idea of this payload. And now we can happily go ahead and run it, and we can run it from outside as well, right? Right. So we have the victim, jump ESP, cat, payload, jump ESP. Okay, you can see here I got a new prompt, which means I'm able to run commands now. Okay, if I exit, I go back to the parent shell. That means I successfully created a shell by escalating the privilege. If this program was running in a privilege mode, the inherited shell, the created shell will have that privilege, at least in the past that was the case. Okay, so you can see that the idea is, even if ASLR is turned on, which is the case in my machine, I just used an address of an instruction called jump star %ESP, if it is present somewhere in the binary, replace the return address by that address, and then put the payload just above the return address, because when ret runs, it will move the stack pointer up. That means the ESP is now just above the return address, and therefore I can happily go ahead and jump there and start executing the code. Okay, so we can also look at this inside GDB to get a better understanding, right? Victim, jump ESP, and disassemble the main. You can put a breakpoint here, after the string copy is done, right? You can even put a breakpoint. Yeah, it doesn't really matter in this case. So let's say we put a breakpoint here, right after the string copy is done, and we run it within the, since payload is already generated, like this, we run it. And now, what am I supposed to do? I can look at ESP or EBB or whatever. Let's look at EBB. ESP is not so much useful at the moment. Let's look at EBB. EBB is going to have knobs. You see here, all these 90s are knobs that we put in. We can look at two words. Okay, what is this now? This means this is the address of the jump star ESP instruction. If you look at the disassembly of this, just above the EBB was return address, right? As you can see, it's jump star ESP instruction. We can put a breakpoint here, which will hit eventually when the red statement runs. As you can see, the breakpoint is hit. It reached the breakpoint. And we can ask, what is the instruction? It should be the jump star ESP instruction. Now we can also look at what is there in the ESP. Let's say 24 bytes, because I know the shell code takes 24 bytes in ESP. You can see all of the shell code starting from 31C0 to CD80. This is exactly the data I placed above the return address. Okay, which means we can even put a breakpoint here. It should hit here and start executing the code. Yeah, we can look at, say, 5 instructions at the current EAP, and we can see all of these were part of our shell code. All right, that's essentially the idea of this return to jump star percentage ESP instruction. Basically, you replace the return address by address of the jump star ESP instruction. This is the jump star ESP instruction, which is part of the assembly. So you grab the address and replace the return address by this address, and you put the shell code above the return address, in this case, for jump star ESP to work. Okay, so even if ASLR is turned on, you are able to successfully exploit. There are some caveats I mentioned. I disabled the stack protector and I made the executable stack permission. Two things you should hardly do that and never do that, most likely in real life. But for the exploit, I am disabling to show to you the value of jumpstar percentage ESP to disable to circumvent ASLR if ASLR is turned on. Okay. We don't have to find the address of the buffer. All we need to know is the address of an instruction like jumpstar percentage ESP. If the attacker has access to the binary, they would be able to get this thing from the binary. Okay, that is the reason why they can generate a payload which can consistently work across multiple machines of the same type. All right, with this, I'm stopping the jumps to ESP attack.